Hello everyone, very good evening. Welcome to the BYJU'S exam prep. So guys, in the today's session, we are going to discuss about instruction formats. So first, let us try to understand that why do we need instruction format. So, but before that, there's an announcement that on 26th of May at 7:30 p.m., Abhinav Negi sir is going to conduct a workshop in which he is going to discuss the complete roadmap to conquer the GATE 2024 exam. So if you are a GATE 2024 aspirant, GATE aspirant, then don't forget to join this workshop. It's a free workshop, so kindly register for this. Now, then there's a brief introduction about me. I have 10 plus years of teaching experience. This is my credentials. My area of expertise are computer organization and architecture, discrete mathematics and graph theory, operating system, database management system, and compiler design. Now, it's moving ahead. So, in the yesterday's session, we have already discussed about instruction cycle, and I told you that there are two parts in instruction cycle. One is instruction fetch, another is execute. So, what actually happens in the instruction fetch? So, let's look at this. So, first we will discuss instruction fetch. We have already discussed. So, let us just give me the brief about that. In this stage, what happens? In this stage, the instruction from memory. From which memory location? Which memory location? Memory, but which memory location? From the memory whose address is present in the program counter register, right? So, the memory address which is present in the program counter register, from that address, the instruction will be loaded. So, when you say transfer, so whenever you store something into the register of a processor, then this is called load. If you store something at a memory address, then this is called store. So load and store, these are two terminologies. If somebody tells you that we are loading something into the CPU, means we are storing some values into the processor registers of the CPU. So, but where exactly that instruction from that memory address will be loaded into the CPU? It will be loaded into the instruction register of the CPU. Clear? So, I have just given you the information that what do you actually need to do in order to load the instruction in the instruction register from the memory address present in the program counter. So what did we say? First of all, the address must be transferred to the memory address register. Why? Because if you want to access a memory, then you need to transfer the address to the memory controller. Now, address can reach to the memory controller only with the help of address buses present in the system bus. But there is only one register in the CPU which can place the address on the address lines, and that register is memory address register. So, though you have the address of the instruction available in the program counter register, but you cannot access the memory based on the value present in the program counter register. First, you need to write that address into the memory address register. From there, it will be placed on the address lines of the system bus. So now, when the address is present in the memory address register, then based on the address present in the memory address register, the content of that memory location will be transferred to the memory data register. Quite enough, already discussed that the data transfer between memory and CPU will take place with the help of data bus. Now, when the address present in the memory address register reaches to the memory controller is eventually going to place the data on the memory data register. On the data bus of the system bus. Memory controller will place the data on the data bus of the system bus. But the only register which is directly connected with the data bus is the memory data register. Therefore, the instruction will first reach to the memory data register. Now, once it has reached to the memory data register, you can simply transfer the instruction from memory data register into the instruction register. Why only in the instruction register? That we will discuss, that the format of instruction is predefined in the instruction register of the processor. Nobody else knows that how many bits, or even if control unit knows that how many bits are there for opcode or to represent the operation, but no other register will have the direct connection with the decoding circuit, so that the operation decoded in the instruction can be operation encoded in the instruction can be decoded. So you must place the instruction in the instruction register. This is it. But what's the concept of instruction fetch? Instruction fetch says that by the time instruction fetch complete, the program counter value will be incremented to point the address of the next instruction. So you eventually need to increment the program counter value. Now what's the idea? If you perform this incrementation operation, try to understand this. If you perform this incrementation operation after you have transferred the instruction from memory data register into instruction register, then you will require an extra cycle to perform this micro instruction, execute this micro instruction. Clear? So extra time will be needed to execute this micro instruction, and this will be required every instruction. So suppose you want to execute 1 lakhs of instruction of a program, then you will have to waste 1 lakh extra cycles in order to execute this micro instruction. Got the idea? Therefore, we will try to figure out if at all this incrementation operation can be done simultaneously with some other micro operation. And yes, because this operation will require only MAR, MDR and system bus, will not require the internal bus of the CPU. Therefore, this micro instruction can be executed, or micro operation can be executed parallelly with this micro operation. So these 2 micro operations will be performed in the same cycle, or will be executed in the same cycle. Very good evening, Sham. Right? So this will save some time. So that's the reason that we are performing this 2 micro operations in the same cycle. That's the logic behind this. Otherwise, you can always execute this micro instruction after this 3rd micro instruction, but it is going to cost you some time. Okay, so this is it. This is what we have already discussed in the last class. Now we need to switch to the execute cycle, right? Now, within the execute cycle, so what's the idea? The instruction is readily available. Once it has been fetched, it is available in the instruction register. Now it is the processor's responsibility to execute the instruction. But for executing the instruction, first we need to decode the instruction. So the very first thing which will happen in the execute phase of instruction cycle is instruction decoding. Clear? Chalo. क्लियर है यहाँ तक सबको? यहाँ तक सारा का सारा सब पिछली क्लास से है, so don't need to worry about anything. Now comes the instruction decoding. Now you need to understand what is instruction decoding. Okay, it's fine that we want to perform various functions in the execute cycle of instruction cycle, but what do you mean by instruction decoding? So let's try to understand this. What is instruction decoding? Read this carefully. Read this very carefully. In this stage, the instruction, which instruction? The instruction present in the instruction register, the instruction which is already in the instruction register of the processor, can be decoded. What do you mean when you say decoded? You need to interpret the information available in the instruction to process that instruction. Got the idea? Arey bhai, what am I trying to say? Let's assume that you have something like 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0. Something is written like this. This is your instruction. Okay, that's fine. Let's assume that this is your instruction, just a 12-bit instruction. But can you tell me anything that what does this binary string represent? No, sir. No. Even CPU will not be able to conclude any information from this binary string if other informations are not already available to the processing unit. So that's the idea, that you need to decode, or whatever information is available in this binary sequence, you need to interpret that information. You need to interpret that. So that's the meaning of decoding. When you say decode, then try to identify that what information is actually available in the encoded format. Okay. Now, who will do that purpose? Who will do the task of decoding? The decoder, instruction decoder. So the instruction decoder are directly connected with the instruction register. There will be a specific set of instruction decoder in the processor, and the only register which will be directly connected with those instruction decoder will be your instruction register. Therefore, we place the fetched instruction into the instruction register. What is instruction decoder? Instruction decoder is nothing but a combination of basically is nothing but a combinational logic, right? और उसका क्या काम है? Combinational logic which will provide the information, the required information to the control unit so that the control unit can generate the required control signal on the control line. What the idea? If it is addition, then it is the job of control unit to generate the control signals which will enable the arithmetical logical unit to perform the addition operation. So let's try to understand. There is a single ALU in the system. That ALU can perform the addition operation, subtraction operation, multiplication operation, shift operation, whatever task you want to perform or whatever operation you want to perform within the ALU, that will be performed with the help of control signals. So if you want the ALU to perform addition operation at this point of time, then who is going to tell the ALU that whatever input is available at your input end, you need to perform the addition on that input? Who is going to inform the ALU about that? So that information need to be transferred by the control unit to the ALU with the help of control signals which will reach to the ALU via control lines, and these control lines are basically the control lines of internal bus, because CPU is generating the control signal, which is control unit is generating the control signal which is a part of a CPU. And these control signals are being generated for ALU. ALU is also the part of the CPU. Now, for the communication within the CPU, the bus which will be used is going to be internal bus. There are two different buses, internal bus and system bus. System bus, you all know, is used for externally connected components. CPU, memory and IO devices are connected externally to each other. But what about the components which are internal to the CPU? For that communication, internal bus will be used. Internal bus will also have, so just like system bus, internal bus will also have address bus, data bus and control bus. Don't worry about that, right? But within the CPU, you don't actually need to transfer the address from CPU. You will transfer the address to the memory or IO devices. Therefore, within the CPU, the transfer of address will occur with the data lines of the internal bus itself. If you want to transfer want to transfer an address from program counter register to memory address register, so though it is an address, but it will travel on the data lines of the internal bus. That this address is not going outside the CPU, it is still inside the CPU, and CPU does not require to send the address to any other circuit within the CPU, because addresses are used for the purpose of memory accessing or for the purpose of IO devices. Clear? So that's the simple logic. So what's instruction decoding? Whatever information is available in the instruction register, you need to decode that information with the help of instruction decoder. Instruction decoders are nothing but the combinational logic. This combinational logic will produce the output which will enable the control unit to generate the control signals on the control lines as required for the execution of that instruction. Clear? So this is the basic definition of instruction decoding. So let me explain this. Let's assume similar situation. Let's assume that there is something like it's a 24-bit instruction. Let's assume it is a 24-bit instruction. 0 0 0 1 0 0 1 0 0 0 0 0 1 1 0 1 0 0 0 0 1 0 1 0. There is something like, so this is your 24-bit instruction. Let's try to visualize this. If you see the last class, then it will be more clear to you guys. So it's a binary sequence, and I'm saying that this is an instruction. Now the idea is you want to decode this instruction. What does it mean? Decoding means you actually want to know that what operation needs to be performed by this instruction. But you don't know where exactly the information about opcode or operation is present in this binary sequence. You don't know this, right? So you have a decoding circuit. You have a decoding circuit. So this is your decoder. Who designed this decoder? Processor designer. Okay. So there is a decoder which will eventually produce the output, and this output is nothing but the operation which needs to be performed. This will produce an output which corresponds to the operation which needs to be performed. But there are various possibilities. Either you can give this 2 bits as an input to this decoder, so it will produce some other output. You can give this 3 bits as an input to this decoder, it will produce some other output. You can give this 4 bits as an input to this decoder, it will produce some other output. You can give this 7 bits as an input to this decoder, it will produce some other output, and so on. So if you don't have any other information about this binary sequence, then you will not be able to process the instruction. So what is needed then? What you need to know is, okay, the processor designer needs to teach the processor that whenever an instruction arrives into the instruction register, then those many bits or those many most significant bits will eventually correspond to the operation defined by that instruction. So let's assume that your processor designer told the CPU that whenever a 24-bit instruction arrives into the instruction register, then only 4 MSB bit will be used to identify the type of operation. In that particular case, once you know that 4 bits are used to identify the operation, so this 4 bits will eventually represent the operation. Who gave this information to the control unit? This information is given to the control unit by the processor designer. So the idea is, you may think that computer is very intelligent and it can do whatever you want, but not so. All of us have understood or have studied one concept in our childhood. What is that? Computer can only do the things which can be done by a human being. The only difference is that computer can do the same thing much faster. Something which cannot be done by a human mind. Let's try to understand. Something which cannot be done by a human mind cannot be done by the CPU. But obvious, you may say, sir, computers are very intelligent. No, because whatever is being done by the computer is taught to the device by a human, which is a processor designer. So if the processor designer himself does not know how to solve a problem, then he cannot teach the computer to solve the particular problem. So that's the idea. I mean, a teacher who does not know the concept of COA cannot teach you the COA. As simple as that. So the processor designer needs to teach the computer how an instruction needs to be executed. So the processor designer must know how to execute an instruction, right? So that's the idea. So this is it. So processor designer knows that there are at most 15 operations supported by the processor. So he will decide that, okay, because there are at most 15 operations being supported by this particular processor, therefore will never require more than 4 bits to represent the operation. So this is it. So he decided that, okay, this 4 bits will go as an input to your decoder. So 4 bit, so it will be now, because processor designer knows that the opcode will be of 4 bit, therefore the processor designer at the design time of the processor will use a 4x16 size decoder. He knows that opcode is going to be of 4 bits, therefore we will use a 4x16 size decoder, and that 4x16 size decoder will be directly connected to the 4 most significant bit of instruction register. This 4x16 size decoder, visualize this 4x16 size decoder will be directly connected to the 4 most significant bits of the instruction register. Now this 4 bits will eventually, so the moment control unit generates a control signal to enable this decoder. This decoder will take the input from the input ends of this decoder and will produce the output. So there are 16 outputs, 16 output lines in this 4x16 size decoder. So one of this 16 line will be enabled with respect to this input on this encoder. So whichever line is 1, so I hope you know the concept of decoder, that if all these are 0 0 0 0, then the line corresponding to pin 0 will be enabled. That is, at 0 you will receive the signal 1, all other will be 0. Now 0 1 2 3 up to 15, right? If the input is 0 0 0 1, then at output if the input is 0 0 0 1, then the line with respect to pin number 1 will have the output as 1, all other lines will have the output as 0. So that's the simple concept. So only 1 based on this input. So 4 can represent exactly 1. 4 bits can represent exactly 1 number out of possible 16 numbers from 0 to 15. So based on this 4-bit input, exactly one of this 16 line will be enabled, all other will remain disabled. Okay. So whichever line is enabled will define the type of operation. Whichever line is enabled, based on that the control unit will decide the operation which needs to be performed. How? At the design time itself, the processor designer will teach the control unit that if the output at pin 0, if the output at pin 0 is 1, then the operation which will be performed is subtraction. If the output at line 1 is 1, then the operation that needs to be performed is addition. If the output at line 2 is 1, then operation which needs to be performed is a multiplication. So this is how the processor designer has decided. Thank you, Pramod. Okay. So this is how the processor designer will teach the control unit about the possible operation which needs to be performed by the CPU based on the information available in the instruction register. Clear? So that's the idea. Okay, so from now, from here, you know that, okay, once we know that how many bits are being used to represent the operation, that's the idea which you need to learn. Once you know that how many bits are being used to represent the operation, then those many information available at those bits can be placed as an input of the to the decoder, and based on the output of decoder you can decide that which operation needs to be performed. Okay, so again some more things which you need to understand. Sir, there may be various type of operations, I mean various types of instruction within the same processor. Yes sir. So let's try to understand this. This is very important. Very important. Samjho. So if I say add I'm taking the example from the last class itself. If I say add R3 and 10, then what does it mean? It means, and the similar situation in which the opcode information requires 4-bit, addressing mode information requires 3-bit, this addressing mode information will also require 3-bit. To represent the addresses you require 10 bits, 7 bits, not 10, 7 bits. Right, so that's the idea. But you can have some other addition operations as well. So like you can actually say add $20. What is this? There is also an addition operation. There is also an addition operation. So is there any difference between these two types of addition? Is there any difference between these two types of addition? Tell me. So let's try to understand one thing. This represents the instruction format. How? Sir, this is an instruction in which there are two address fields. There is one address field along with its addressing mode. There is another address field along with its addressing mode. But in this particular example, there is only one address field. So if it is a one address instruction, it will be executed in a different manner. If it is a two address instruction, it will be executed completely in a completely different manner. So if I say, how do we execute this instruction? The behavior of this instruction says that add the content of R3 with the content available at memory location 10 and store that content into the register R3. That's the meaning of this first instruction. What is the meaning of this second instruction? This second instruction is the one address instruction. We will understand in a while about all these different types of instruction. But in one address instruction, so see, for any binary operation, two operands are required. For any binary operation, two operands are required. But in this particular scenario, there is only one address field, and at one address field, you can store only one operand. So what about the second operand? So in this scenario, the second operand is by default available in a special purpose register of the CPU, which is known as accumulator register. So the content, whatever content is available in the accumulator register, will be added with the content available at memory address 10. So you will add the content of memory location 10 with the content of accumulator, and in this scenario, by default, the result will be stored in the accumulator. By default, the result will be stored in the accumulator. Apart from this, you can have one more format as well. You can say, sir, just write add R0, R1, R2. So what is this? So this is an instruction in which there are three address fields. This is one address field along with its addressing mode, another address field along with its addressing mode, and this is the third address field. Now, what is the interpretation of this particular instruction? For this instruction, in 3 address instruction, one of the operand will behave as destination, another 2 will behave as source. Means, and in general, if you see any instruction like this, then generally this may be different as well if it's specified in the question, but generally the first register in the 3 address instruction will represent the destination and remaining 2 will represent the source. So what will happen? You need to add the content of register R1 with the content of register R2. So you need to add the content of register R1 with the content of register R2, and you need to store it into register R0. Sir, what are you trying to say? I am trying to say that here, if you know from the last class, then this is actually nothing but register addressing mode. These 7 bits are representing register number because it is the register addressing mode. So this 7 bits are representing the register number. Next 3 bits are representing direct addressing mode, and remaining 7 bits are representing memory address 10. This is from the last class. Okay, so this is the scenario. But here the problem is, this is the addition operation. You have seen, you have given this 4 bits as stored by the processor designer to the decoder, and the decoder is saying that this is the addition operation. So what does it mean? So this is also addition, this is addition, this is also addition, this is also addition. So which type of addition you are talking about? Which type of addition you are talking about? This information is also available to the control unit based on the output of the decoder. So what does it mean? It means this is a deeper concept which we'll try to understand with the help of some questions, but at this point of time only try to understand one thing. So if these 4 bits are telling me that this instruction is with respect to addition operation, then tell me whether this addition is with respect to this first type of instruction, this addition is with respect to this second type of instruction, or this addition is with respect to this third type of instruction. 3 different possibilities. Let's assume every address field is of 7 bit. Let's assume every address field, whether it is the name of the register or whether it is the memory address. For the simplicity, let's assume that every address field is of 7 bit. So, sir, the size of the instruction is only 24 bit. Size of the instruction is only 24 bit. 4 bits are representing the opcode. If we say that this is a 3 address instruction in which there are 3 addresses, then can you actually represent 3 different addresses using only, can you represent 3 different addresses using only 20 bits where every address is of 7 bit? No, sir. Minimum 21 bits will be required to represent 3 addresses if each address is of 7 bit. Yes, clear. And apart from that, addressing mode information also needs to be incorporated. Yes. So if this is the specification in which every memory address is of, or every address is of 7 bit and opcode is of 4 bit, then our 24 bit instruction can never represent a 3 address instruction. That is an instruction in which there are 3 different address fields, but it can either represent a 1 address instruction or 2 address instruction. So now comes a new situation. If it is a 1 address instruction, then you know that this is your opcode, that is, it will define the operation. And you also know that apart from that, 3 bits are required to identify the addressing mode. So you came to know that these are the 3 bits, and 001 tells me that this is the register addressing mode. Okay. Then what else? Then anything else which is available in the system, must represent an address, right? Because there is, if this is a one address instruction, then one opcode field will be there, one address field will be there, and corresponding to that address field, one addressing mode field will be there. As simple as that. So in this particular scenario, if we say that this 001 using 3 bit represents the register addressing mode, then all these bits will be treated as a address, and this address is obviously more than 128. The value represented by this 17 bit is obviously more than 128, and if I am saying that every address is of 7 bits, then there are not more than 128 cells, because using 7 bit you can represent only 128 cells numbered from 0 to 127. So is it possible? No sir, this is also not possible. So it actually represents the instruction of first type. So sir, you are able to say so because you already know the format of the instruction. But how does a computer or a control unit comes to know about a particular type of format being used in the given instruction? For that, the processor designer again uses an approach which is known as expanding opcode technique. What happens in that? So, do you realize that there is a situation in which if the instruction is a 0 address instruction, or 1 address instruction, or 2 address instruction, or 3 address instruction, in different representation, the number of bits available to define the opcode will be different. How? So if it is a 0 address instruction, all 24 bits will be used to represent only one information, that is the operation. So this 24 bits together will represent the operation only, because no address field is required. If it is a 1 address instruction, then you will eventually require certain bits to represent the address and certain bits to represent the addressing mode corresponding to that address field. All other bits can be used to represent an operation with respect to 1 address instruction. Similarly, if it is a 2 address instruction, then you will require 1 address field, 1 addressing mode, another address field, another addressing mode, and the remaining bits can be used to represent a 2 address instruction. So this is already known to the processor designer that okay, address will be of X bit, addressing mode will be of Y bit. So if address is of X bit, addressing mode is of Y bit. Now the idea is, if it is 1, and let's assume the total length of instruction is equals to L. Total length of instruction is L. So if this is the scenario, then in 0 address instruction there will be only one field which will be opcode. Clear? So in 1 address instruction, all L bits will be used to represent the opcode. How many bits will be used to represent the opcode in 1 address instruction? So you will require 1 address and 1 addressing mode. That is, L are the total number of bits available in an instruction. Out of those, X will be used to represent the address and Y will be used to represent the addressing mode corresponding to that address. This is the general scenario. Things may vary based on the question. So X plus Y bits will be used to represent 1 address and 1 addressing mode. So those many bits cannot be used to represent the opcode. Remaining L minus X plus Y bits can be used to represent a opcode with respect to one address instruction. So with respect to 0 address instruction, all L bits will represent a opcode. In one address instruction, L minus X plus Y bits will represent the opcode. In 2 address instruction, you will require 2 addresses, that is 2x bits for address, and 2 addressing mode, that is 2 times of Y bits for addressing mode. That is, out of L, 2 times of X plus Y bits will be used to represent the addresses along with their addressing mode. Therefore, only those many bits will be available to represent the opcode. In 3 address instruction, you will eventually require 3 addresses and 3 addressing mode. Therefore, in 3 address instruction, L minus 3 into X plus Y bits will be used to represent a opcode. Now let's see. If you look at the size, then L is the lengthiest one and L minus 3 into X plus Y is the shortest. This is the shortest. This is the lengthiest. Right? So, for 0 address instruction, the length of the opcode will be more. For 1 address instruction, the length of the opcode will be comparatively less. For 2 address instruction, length of the opcode will be even lesser than 1 address instruction. And for 3 address instruction, length of the opcode field will be shortest. Got the idea? So, okay. So, this is it. That's why I have taken the empty slide. But one more thing which you need to understand. Now you know that this is the scenario that just addition does not give any information that what type of addition needs to be performed by the ALU. Therefore, you need some other information as well. What information? That if you want to perform the addition, then this addition represents which type of instruction. Whether this addition is with respect to an instruction which requires only 1 address field, or an instruction which requires 2 address field, or with respect to instruction which requires 3 address field. So that's what we need to represent. Now let's see the idea. Processor designer already know that for 0 address instruction, I can use a larger opcode field. For 3 address instruction format, the length of the opcode field should be minimum, because the instruction needs to accommodate 3 address field and 3 addressing mode. It also along with that particular addresses, with those particular addresses, right? So that's the idea. Now let's assume that this processor, whatever processor, let's assume that this processor supports 0 address instruction as well as 1 address instruction as well as 2 address instruction. Let's assume this processor supports 0 address instruction, 1 address instruction and 2 address instruction. So for 0 address instruction, very important, for 0 address instruction, no field will be required to represent the address. That is, for 0 address instruction, all 24 bits can be used to represent the opcode, right? Similarly, if it is a 1 address instruction, then obviously 1 address field and 1 addressing mode field corresponding to that will be required. Therefore, opcode field will be of 24 minus 3 plus 7, that is 14 bit. Clear? Similarly, if it is a 2 address instruction, then processor designer know that the total size of the sorry guys. Processor designer will know that the total size of the instruction is 24 bit. Out of those 24 bit, 3 bits will be required for addressing mode, 7 bits will be required for address, and because there are 2 addresses, therefore this 3 and 7 bits will be required 2 times. So what will it be? So it will be 20. So 24 minus 20, that is only 4. So the processor designer, once the processor designer knows that how many bits are used for addressing mode, how many bits are used for address field, it can eventually identify that how many bits will be available for 0 address instruction, how many bits will be available for 1 address instruction, how many bits will be available for 2 address instruction. So that's the idea. So if this 4 bits, let's try to understand further. Initially, the control unit will start with the highest format supported by that processor. Initially, the control unit will start with the highest format supported by that processor. What do you mean when I say highest format supported by that processor? Let's assume that the processor supports 3 different instruction format: 0 address instruction, 1 address instruction, and 2 address instruction. So what will happen? Now the highest address format is 2 address instruction format. Therefore, first of all, control unit will start decoding this instruction by assuming that this is a 2 address instruction, and based on that, the control unit will know that if it is a 2 address instruction, then out of 24 bits, 20 bits will be used to represent 2 different addresses and 2 different addressing modes. Therefore, only 4 bits will be available to represent the opcode corresponding to that 2 address instruction. So it will first decode this 4 bit. If this 4 bit pattern, if the output corresponding to this 4 bit is the valid 2 address instruction, now comes a new term, valid or invalid. So I am saying that my processor supports 16 instruction. Does it mean that overall 16 instruction? No, sir. So maximum 16 2 address instruction. What do you mean when you say maximum 16 2 address instruction? It means to say that we can have, using 4 bit, we can represent 16 different opcode patterns. We can represent 16 different opcode patterns, and for all those 16 different opcode patterns, we'll have the capability to provide 2 address fields and 2 addressing mode fields. But let's assume that your processor designer comes to know that this is fine, that we can support 16 different operations in which 2 address fields are available. But he comes to know that no, I actually want to support only 3 different type of operation in which 2 address fields are allowed. Try to understand this. The processor designer decides that my processor will support only 3 different operations with respect to which 2 addresses are allowed. Otherwise, it will not be a 2 address instruction, it will be a 1 address or 0 address instruction. What does it mean? The processor designer decides that, let's assume that processor designer decides that I want to support only 3 instructions, 3 2 address instructions. 3 2 address instructions. What are they? Addition, subtraction, and multiplication. Let's assume for subtraction the pattern defined by the designer is 0 0 0 0. Let's assume for addition the pattern defined by the processor designer is 0 0 0 1, and for multiplication the pattern defined by the processor designer is 0 0 1 0. So what does it say? processor will eventually start by assuming that this instruction is a 2-address instruction. So the control unit knows that if it is a 2-address instruction, then opcode will be of 4-bit. So this 4 bits will be given to a decoder. If the output corresponding to those 4 bits correspond to either 0 or 1 or 2, then only these operations are considered valid. Otherwise, this 2-address operation is considered invalid. What does it mean? It means, let's assume, if it is 0001, then this 0001 will go to the decoder and it will enable the line corresponding to the pin number 1, and because pin number 1 is associated with the valid addition operation, therefore the control unit will come to know that yes, it is an addition operation, and because this 4-bit pattern is with respect to 2-address instruction, because this 4-bit opcode is with respect to 2-address instruction, therefore control unit will also know that after this there are 2 address fields, and corresponding to those 2 address fields there will be 2 addressing mode fields as well, right? So the moment the control unit comes to know that 0001 is a valid 2-address addition operation, then it will consider the next 3-bit as addressing mode, it will consider the next 7-bit as address field corresponding to the first address, the next 3-bit it will consider as addressing mode for the second address, and the next 7-bit will be considered as address corresponding to the second operand. This is it. Now, but what happens if this pattern is somewhat different? What does it mean? Let's assume that something wrong happened. Okay. Let's assume another thing. Let's assume the programmer is actually writing a statement in which he is trying to represent add 20. So now the idea is, if the programmer is writing an instruction in which there is only one address field, then at the time of compilation, when with respect to this assembly language instruction, the backend of the compiler will eventually try to generate the binary code which is with respect to this instruction. Yesterday, in the yesterday's class, we have seen that the compiler is trying to generate the binary code with respect to instruction add R3, 10. If this is the instruction and this is for addition with respect to 2 address addition, if the opcode is 0001 with respect to register addressing mode, if the pattern is 001, and with respect to direct addressing mode, if the pattern is 010, then this is how your compiler will, or your target code generator will eventually generate a binary sequence with respect to this instruction. But if this is the instruction which is given to the target code generator, then the target code generator will eventually identify that okay, this is the addition, but this is the addition in which there is only one address field. This is an addition in which there is only one address field. Therefore, now only one address field. So the backend of the compiler is machine dependent. So backend eventually know that if the instruction consists of only one address field, then how it should be converted into binary. So backend knows that my processor can support one address instruction. Backend knows that my processor can support 0 address instruction. It also knows that my processor can support zero address instruction. So that's the idea: zero address, one address, two address. So if the backend see the instruction as a two address instruction, then this is how the assembly language instruction will be converted into binary. But if this is the assembly language instruction given to the on target code generator, then ultimately the target code generator will observe that there is only one address field. Therefore, to represent this 20, 7 bits will be needed. To represent this direct addressing mode, 3 bits will be needed, and no other extra field in this instruction. Therefore, apart from this 10 bits, 14 bits will be available to represent the opcode. 14 bits will be available to represent the opcode. Means, and this 14 bits will eventually be of the type which do not coincide with any one of the valid two address instruction, right? So means in those 14 bits, the first 4 bit cannot be 0000 or 0001 or 0010. The first 4 bit among those 14 bits can be anything else but this 3 pattern. These 3 patterns are not allowed in those 14-bit patterns. So let's assume that this is the addition which represents a pattern in which first 4 bit is obviously different from this. So let's assume that the first 4 bits are like 1010. But that's okay. But we have some other bits available as well. So 0101 1100 11. Let's assume that this is the pattern. Let's assume that this is the 14-bit pattern which represent a one address addition. Let's assume this is a binary pattern corresponding to one address addition. So because the object code generator see that the assembly language instruction is a one address instruction, therefore this addition will not be converted into binary pattern based on the addition with respect to two address instruction, but this addition will be converted into binary pattern with respect to binary pattern with respect to one address addition operation. Got the idea? So let's assume that processor designer decides that whenever the operation is one address addition, then the equivalent binary pattern is this. Then with respect to this, what information will be inserted in the binary instruction? So initially addition will be represented by this 14-bit. Then you need to represent the addressing mode. Addressing mode is direct addressing mode, and for direct addressing mode, if we are using 010, then apart from this 14 bits, the next 3 bit will represent 010. Next 3 bits will represent 010, and to represent 20, there is one more 0 after this, not enough space. Oh, what's happening? Okay, I did not cancel this. Thank God I did not lose these slides. What's wrong? Just a minute, guys. we are back. So, this is good. I'm not able to erase this. I can write some new things. Just a minute. I'm not able to delete that portion. If I'm writing something here, then I can actually perform any operation, but on that I cannot perform any operation. Okay, this is the slide, this is the annotation. Anyway, I'll handle that. Thank you. Okay guys, something went wrong in between, therefore this thing is permanent. Let me remove this. Okay, so let's start further. Now, what's the idea? Let's assume that for direct addressing mode we are writing 0, 1, 0, and to represent this 20, we'll eventually use 0, 0, 1, 0, 1, 0, 0. So this is your 20. So this will be the complete instruction. This will be the complete binary instruction with respect to this assembly language instruction generated by the object code generator or binary code generator. Clear? So this is the idea. Now let's see. Sir, what happens if this instruction, if this is a valid to address instruction format, if there is a valid to address instruction format and this instruction is given to the control unit, then first of all the control unit will try to see whether this is a valid to address instruction or not. So first of all, this 4 bits will be given as an input to the decoding circuit. Based on the output, if it is a valid 0001 is a valid to address instruction, therefore the control unit will come to know that yes, this is a addition operation in which there will be 2 address fields, right? But if this is the instruction given, to the control unit, then control unit will try to identify whether this is a valid. Control unit will try to identify whether this is a valid to address instruction or not. What did I say? The control unit will first try to see whether the available instruction is a valid highest level instruction or not. So if the CPU supports 0 address, 1 address and 2 address instruction, then the control unit will first check whether it is a valid 2 address instruction or not. So for 2 address instruction, the opcode will be of 4 bit. So first of all, this 4 bits will be given to this decoding circuit, which will again be a 4x16 decoder. Based on this, which will get an output. This 4 bits does not represent 0000 or 0001 or 0010. So with respect to this decoder, neither the output corresponding to the pin 0 will be 1, neither the output corresponding to pin 1 will be 1, nor the output corresponding to pin 2 will be 1. That is, this is not a valid to address instruction. Now, once this control unit comes to know that this is not a valid to address instruction, then it will say, the object code has given me a binary sequence. It should be corresponding to one of the instructions. So the control unit will start thinking that if it is not a valid to address instruction, then perhaps it is a one address instruction. So then it will try to calculate that if it is a one address instruction, how many bits will be available in the opcode field. I just told you that if it is a one address instruction, then out of total available bits, L minus X plus Y, that is total number of bits minus number of bits required for the addressing mode plus number of bits required for the address field, will be available for the opcode. So there are overall 24 bits. Out of those 24 bits, how many bits? 3 for addressing mode and 7 for address. 10 bits will not be available for opcode. All other bits will be part of the opcode. So among this 24 bits, apart from this 10 bits, all other bits will be treated as an opcode for one address instruction format. Now what will happen? All this ten bits, all this 14 bits, apart from 10, all this 14 bits will be given as an input to a 14 cross 2 cross 14 size decoder, will be given to one of the 14 cross 2 cross 14 size decoder, because based on the 14 input lines, there are 2 raised power 14 different outputs possible. So obviously this is not, and this 14 bits does not represent any of the valid to address instruction format. So we are checking whether this 14 bits now represent a valid one address instruction format or not. So based on this output, so let's try to understand, because this pattern is with respect to a valid one address addition. Therefore, from here you will get a valid opcode, valid operation addition. So now you will come to know that this binary sequence actually represent a addition operation in which there will be only one address field. So for different addition, so what am I trying to tell you? For different addition, the binary patterns will be different. For different addition, binary pattern will be different. If the operation is add R3, 10, if the operation is add R3, 10, then with respect to this addition, this is the binary pattern. But if the operation is add 20, then with respect to this addition, the binary pattern generated by the object code generator will be this. So there will be no ambiguity to the control unit in deciding whether the addition, that's okay that this is an addition, but there will be no ambiguity in deciding whether the addition is with respect to two address instruction or one address instruction. Now, last and most important thing, once the control unit comes to know that this operation is a valid operation, then it will also come to know that how many address fields are there in the instruction. If there is only one address field, then according to that, this 3 bits will be given to decoding circuit to decode the encoded addressing mode, and this 7 bits will be given to identify the value present in the address field. If the control unit comes to know that this is a 2 address addition, then this 3 bits will be given to one decoding circuit which will decode the addressing mode for the first operand. These 3 bits will be given to another decoding circuit which will decode the addressing mode for the second address field. Similarly, the value represented by this 7 bits will represent the address information with respect to first operand. This 7 bits will represent the address information with respect to second operand. So that's how the things are going to work. So that's okay. Instruction decoding. If you simply try to see what is the instruction decoding, then anyone can give you the definition that instruction decoding is a process in which we try to identify the operation which needs to be performed by the instruction. It doesn't teach you anything. Okay. So like if you want to study the subject in that particular manner, that okay, instruction decoding is nothing but a process in which we try to interpret the instruction, or the process in which we try to identify the operation which needs to be performed corresponding to that instruction, then this is just a definition. You can happily live with that. But you need to understand that what is the internal working of the CPU with respect to any binary pattern. So all this information are taught to control unit and CPU by the processor designer, that how many bits will be there in the opcode field with respect to 2 address instruction, how many bits will be there in the opcode field with respect to 1 address instruction. So based on this opcode, whichever bit is 1, the control unit will also come to know whether this is a 2 address instruction or 1 address instruction or 0 address instruction, or for that sake 3 address instruction if it is supported by the control unit. Clear? So this is it. That's one thing. Let's move ahead now. Now instruction formats. So if we talk about the instruction format, then there are 4 different instruction formats. One is 0 address instruction, 1 address instruction, 2 address instruction, 3 address instruction. So instruction formats does not specify anything else but a single thing, that how many address field will be present in that instruction. Every instruction must have opcode field. Every instruction must have opcode field, but there may be no address field or multiple address field in a single instruction. So no matter what, opcode field will always be available in every instruction, but addresses may or may not be present. So if there is no address information present in the instruction, then this is called 0 address instruction. If there is exactly 1 address present in the instruction, then this will be known as 1 address instruction. If there are 2 addresses present in the instruction, then 3 address instruction. If there are 3 addresses present in the instruction, then 3 address instruction. So let me give some examples of different types of instruction. If I say, have you ever heard this instruction STC? This is nothing but this is a mnemonic which says set carry flag. Do you need to provide the address of the carry flag to the CPU? No sir, it is very well known to the control unit or and CPU that where exactly carry flag resides in the system. You don't need to pass any address. Similarly, complement accumulator or other type of operations. So in the complete instruction, if we think of 0 address instruction format, then in the complete instruction, one and only one information will be specified by that instruction, and that information will be nothing else but opcode. That what operation needs to be performed, only that information will be specified by the 0 address instruction. Now comes the 1 address instruction. In 1 address instruction, as the name suggests, that there will be exactly 1 address field. There will be exactly 1 address field. So just like, let me write an example. If I say add $20, so what does it mean? Interpretation of this is content of accumulator will be added with the content of memory location 20 and the result will be stored in the accumulator. Now, why so? See, if the instruction is one address instruction, then obviously we know that for any binary operation we require at least two operand, but we are providing only one address. What does it mean? That okay, we are providing you one operand, but another operand is implicitly available in the CPU. Where? So the moment CPU comes to know that it is a one address instruction, then CPU will realize that okay, if it is a one address instruction, then he is providing me the address of the second operand, but first operand is by default available in the accumulator, and the programmer need not specify the address of the accumulator to the control unit, because the address of the accumulator is already known to the CPU. It is inside the CPU itself. So you don't need to provide that which accumulator or which register. CPU knows that there is only one accumulator and the address of that accumulator is known to the CPU. Now, what happens? If it is a one address instruction, then in the instruction, if this is your instruction, then within the instruction, obviously in every instruction there should be opcode information, just like in this instruction addition is there. So to represent addition, certain number of bits will be present in the instruction. Apart from that, the remaining bits will be used to represent one address. Remaining bits will be used to represent one address. Now see, we have just discussed about the addressing mode. So if given, we will also consider the addressing mode field for that address. If given, then we will also consider the addressing mode field for that address, that how exactly the information present in that address field should be treated. But if nothing is given, then all these bits will be considered for the address. So in the question, so in actual addressing mode field will always be present, because you need to specify that whatever information is available in the address field, how that information should be treated to identify the effective address. But from the numerical point of view, in GATE exam, for many of the question, there will be no information. In many of the questions, there will be no information about addressing mode field. So in that scenario, you need to consider only address fields within the instruction. You don't need to give the weightage, or you don't need to use certain number of bits to represent the addressing mode information. Okay. Similarly, if it is a two address instruction, then in two address instruction, let's assume this is your example, add R3 10. So there are two addresses. So now we know what is the interpretation of this. The interpretation is that by default in two address instruction, the first address will be used as a source as well as destination. So R3 will be used as operand 1. So the content of operand, so the operand 1 will be added with operand 2. For operand 2, it is a direct addressing mode. Therefore, directly the content of memory location 10 will be your operand. Now, the result will be stored where? In one address instruction, the result is stored in the accumulator, because this is by default working for one address instruction. But for two address instruction, the result will be stored in the first operand itself, that is R3. So the result of R3 plus content of memory location 10 will be stored in register R3 after the operation. Now what? If you think of the instruction, then simple. If it is an instruction, then there will be three fields. There will be three fields. One is the opcode, obviously, and because it is a two address instruction, therefore there should be two address field. This is your address 1 This is your address 2. Good enough. Address 1 and address 2. If nothing is given in the problem, then we will consider the addresses, we will consider the fields only to represent the addresses. If information about the addressing mode is also given, then we will consider the bits for addressing mode with respect to addressing address 1. We will also consider the second addressing mode field for address 2. If it is given. If no information is given about addressing mode, then we will not consider the field in the instruction for addressing mode. Similarly, 3 address instruction, it is the type of instruction in which 3 different address fields will be present. Anything. So in this scenario, if it is a 3 address instruction, one of the address will work as a destination, remaining 2 will work as a source. Therefore, in general, in 3 address instruction, the first address will work as destination address, the remaining 2 will work as source address. Therefore, this is the source 1, this is the source 2. Therefore, content of R1 will be added with the content of memory location 30, and the first address will work as destination. Therefore, this result will be stored in the register R0. Result will be stored in register R0. Now again, if it is a 3 address instruction, then it says that there will be 3 address field in the instruction. Within the instruction, one opcode field must be present. It is mandatory. Opcode is necessary in all the instruction. But apart from that, if it is a 3 address instruction, then there will be 3 address fields. Again, if nothing is given about the addressing mode, you don't need to consider the fields for addressing mode. If information is given about the addressing mode, then you will have to consider the fields for addressing mode as well. Not mandatory. This fields needs to be considered only if the information is given in the question. Otherwise, you don't need to consider them. Clear? So these are the 4 different instruction format. To have the better understanding of this concept, I will try to discuss some problems with you, that how a 2 address machine can also support 1 address instruction or 0 address instruction. A machine can support 2 address instruction and 0 address instruction, but no 1 address instruction, and how many such lower level instructions can be supported. That is, let's assume if there's an instruction. For an example, let's try to think of this. For example, let's assume that there's a 24-bit instruction. Number of bits required for address are 6. This is the number of bits required for address are 6, and the last thing which I am saying is processor supports two address and 1 address. This is your homework. Try solving this question. So what am I saying? There is a 24-bit instruction. 6 bits are required to represent 1 address. Processor supports 2 different types of instruction format, 2 address instruction and 1 address instruction. Now, if I tell you 12. Next thing is, if processor needs to support processor needs to support 500 2 address instructions. if processor needs to support 500 to address instructions, then how many one address instruction can be designed? How many one address instruction can be supported or can be formulated? In that processor. Got the idea? So, what am I trying to say? That you have a 24-bit instruction. Let us just think of it. So, you have an instruction in which total number of bits available are 24-bit. Now, it supports 0 address and 1 address. So I'm saying it is if it is a 2 address instruction, then there is your address 1, there is your address 2. For this you will require 6 bit. For this field as well you will require 6 bits. So for both the address fields you will require 6 bits. Now nothing is given about the addressing mode, so you can skip the addressing mode information. Now out of 24 bits, if 12 bits are gone for 2 different addresses, then how many bits are left for opcode? Sir, the number of bits left for opcode are 12. So using 12, how many different operations can be defined? Sir, using 12, 2 raised to power 12, that is 4096. Using 12, 4096 different operations can be formulated, because there are 4096 patterns of 12-bit. Corresponding to each pattern you can define one operation, but the processor designer know that my processor needs only 500 to address instruction. I will not require more than 500 to address instructions. So among those 4096 possible patterns of 12-bit, 500 can be used for to address instructions. So we are left with how many? We are left with 3596 patterns which are not used for any of the to address instruction. Now my question is, if there are so many free patterns which are not used to define any valid to address instruction, then how many total combinations are available to define a 0 address instruction? Think of this, then we will try to see the solution for this. So this is it. This is your instruction format. That's all. So this is the end of the instruction format as a basic. From the numerical point of view, we may see some questions related to this, but for now, this is it. So guys, this is it for the today's session. Now there are some announcements. There are various series going on the YouTube. There is a series going on with the name GATE 2024 Fundamentals NIELIT series. This is going on Monday, Wednesday, Friday and Sunday. Very important, because vacancies has been published by the NIC. ISRO series is going on. The recorded series Copy with Concept and Learn with Fun are also going on. So kindly, if you like the video, then kindly hit the like button. For watching the other videos and to watch the other series, do subscribe the channel and press the bell icon to get the notification about upcoming videos. This is it. Thank you very much guys for today's session. See you tomorrow. Good night. Take care.